Hi everyone. Today we are excited to have Professor Justin Thaler with us. Let me start with a brief introduction about him. Professor Thaler is an associate professor at the Georgetown University in United States of America. He completed his PhD at the prestigious Harvard University and was also a research scientist at the Yahoo Labs for 2 years. Thank you, Professor Justin, for joining with us today. And let us dive directly into the questions. So the first question would be, what are your research interests? And maybe can you explain your research interest to our audience, which is majorly high school students and undergraduates?
Yeah, sounds good. I'm excited to be here for this today. I can try to explain. So I generally focus on three different areas. So the first is something called verifiable computing. The second is sort of a specific sort of mathematical notion called approximate degree, which has a bunch of applications in theoretical computer science. And the third is streaming algorithms. So I guess I have to sort of say something about each of them. So with verifiable computing, the goal, broadly speaking, is to allow a computationally weak verifier to interact with a powerful but untrusted prover. And the prover is going to make a claim to have run some sort of computation that's maybe beyond the capabilities of the verifier, or perhaps to know some sort of witness, some sort of string satisfying a property, that, and the verifier doesn't know such a string, and the prover needs to prove to the verifier that it knows this information. So, as an example, when I started working on this, the example everyone sort of talked about, which doesn't really capture how people are using these today, is somebody could hire, say, a cloud computing service like Google or Amazon or something to, run a program of theirs using, the giant computing cluster maintained by the cloud, and the cloud will go and run the program using massive compute resources and come back and says, hey, here's the output of your program. I ran your program on your data. Here's the answer. And the question is, like, what if the user doesn't trust that the cloud did everything correctly for whatever reason? Maybe even the cloud is deliberately trying to trick the user. And so these verifiable computing would let the user sort of get a guarantee that the answer is correct. And the work that the user does to check the claim and get this guarantee is just tiny, is vastly less than the work that the cloud did. So that was the application we thought about when I sort of started working on this. But now this has sort of evolved, and people are particularly excited about these protocols in the context of public blockchains and ensuring that they can process many more transactions than they're processing today. So that's one topic, and maybe there'll be a chance to say a little bit more about that later in the conversation. The second thing I work on is a particular mathematical notion, asking how well certain functions people are interested in can be approximated by low-degree polynomials. So that's a technical sounding thing, but maybe it's more interesting to mention some of the applications it has in theoretical computer science. So I guess one that I find particularly exciting and important is to quantum computing. So a major research goal that there's a lot of work left to do on is to understand what kinds of problems quantum computers will be useful for once we actually have scalable quantum computers that people are really working hard to build right now. It's known that quantum computers can factor numbers efficiently, and most people don't believe that classical computers can do that. There's a lot of crypto systems based on that assumption, but beyond that, it's not super well understood what quantum computers will actually be useful for, solving problems faster than classical ones. So it turns out that any function that can be computed quickly on a quantum computer is in some sense approximable by low degree polynomials. Okay, so what that means is if I'm actually able to show that a particular function cannot be approximated well by low degree polynomials, we can conclude there is no efficient quantum algorithm. So, I spend a lot of time trying to show that, some particular function, people care about for whatever reason actually can't be well approximated by low degree polynomials. And then we're able to conclude that in some sense, it's a difficult function for quantum algorithms. And that's kind of a way I can potentially, say interesting things about quantum computing just by studying polynomials. So I basically don't even have to understand quantum mechanics in any way. And then the final thing I work on is streaming algorithms. So this is algorithms targeted at settings where you have a whole lot of data. So much data that either you can't store it all, or even if you can store it, you don't want to have to go back and read all of it again every time someone asks a new question about it. These algorithms are actually useful even if you don't really care about data storage and all that, like just for system design, because these algorithms often enable you to do the following. You can take a giant input set, you can break it up into pieces however you'd like. You can run the streaming algorithm on each piece independently. So this is like automatic parallelization and distribution of the computation. So each streaming algorithm is going to wind up producing just a little tiny summary of the data it analyzed. And then it's often possible to just merge all those summaries together to get a summary of the entire data set. So as a result, you're able to automatically process massive data sets in a distributed and parallel manner. Whereas if you weren't using a streaming algorithm, and these algorithms, they make some errors, but we carefully analyze and control the amount of error they're introducing. And for many of these problems, if you're trying to solve them exactly, they'd be very difficult, even impossible potentially, to parallelize and distribute in this manner. So even ignoring like data storage, these algorithms can be really important for systems reasons. Okay, so those are my three main focuses. Hope those explanations were somewhat understandable. And yeah, maybe there'll be a chance later in this conversation to elaborate on some of them.
Yeah, definitely. Thank you. Thank you for such a beautiful explanation. I think our audience will definitely get this idea. So maybe, as you said, we can elaborate a bit more on these topics. So maybe I can ask you, what is the central goal in each of these fields? So you mentioned about verifiable computing, and you mentioned about approximate degree and streaming algorithm. So what is the central goal which people are trying to approach the problem towards? And maybe and related question is like, how much progress do you think has been made so far, and how much work is still left?
Yeah, sure. So I guess, I'll go through each one in turn again. So with verifiable computing, there are some really interesting, wide open theoretical questions, like super fundamental. But for me, my focus these days is actually on the practical side of things. So when I started working on verifiable computing, so it's been known since the late 80s. So what is that, 30 years now or something? Maybe more.
40.
Yes, that in theory, like in principle, there are like extremely efficient, like surprisingly complicated statements can be proven to an efficient, like very computationally limited verifier. But when I started my PhD 10-ish years ago now, or something like that, it was believed that these protocols were wildly impractical. And I mean, really, if you were to implement them as they were presented in their original works, like the prover in these protocols would take trillions of years, like even for short, really simple statements being proven. So there was a whole lot of work kind of when I was just starting out, to take these wildly impractical protocols and make them like plausibly practical, like people could actually, run the protocols on, kind of toy problems, but meaningful statements. And so that it was a really exciting time to be working on it, because, it's really cool to go from totally impractical to, we've got code running, like, let's think about this. Now there's just an explosion of interest in these topics because people have started to apply them for blockchain scalability applications. So, these are deployed like today, but they're still significantly more expensive than would be ideal. I mean, you can always make things more efficient, but I think the cost of these protocols are still high, despite them being deployed today. So yeah, I think a central goal for my focus right now, especially, is to just make these more concretely efficient. And the protocols I've worked on to date, they tend to be have really nice, like kind of the best efficiency for the prover, but are more expensive than alternate approaches for the verifier. And I'd really like to kind of address the downsides and sort of get the best of all worlds. So that I think is a major cool direction, to sort of take the stuff that's really good for the prover and take the stuff that's really good for the verifier and somehow put them together to get something that's really good for everyone. Okay, so that's verifiable computing. I hope that's understandable explanation.
Yes.
So for streaming algorithms, I have a particular focus. Like there are very interesting theoretical questions here, but this is another research area that I've sort of taken an applied approach in recent years. So I'm involved with a certain open source library of streaming algorithms called Data Sketches, and this library, the algorithms in it are only capable of answering like very, very simple questions about the data. So questions like, what's the most frequently occurring item in the data set? Like if it's a bunch of search queries typed into a search engine, like what's the most popular search terms or something. Things like quantiles queries, you get a big string of numbers and, what's the median number approximately. So really, really simple questions, but these are questions people need to answer all the time on huge data sets. We can always make these sketches more efficient. Like even for these simple queries where they're highly studied and pretty well understood. But then I think it's really interesting if you move to slightly more complicated questions about the data, like maybe you want to understand, do some kind of matrix analytic computation on your data. You have vectors describing, could be anything, and you want to understand like what the most important, features in the data are. That kind of boils down off into a matrix analytic question. And those algorithms are just concretely much more expensive to run than something as simple as like a frequent items algorithm. So I think, like the Data Sketches library, for example, has some matrix analytic algorithms. They're just more expensive, and we'd love to have more. So I think that's bridging that gap from sort of the theory of those algorithms, which is really beautiful and quite well developed, to the being able to run them on the sorts of data sets people are currently using this library on is really juicy question. Maybe I'll stop there, skip the approximate degree, since I keep going on and on. Yeah.
So I guess maybe my next question was if you can tell us something exciting applications of the research work in daily life, but I guess you have already answered them in the previous two questions. But do you want to add something more, some maybe exciting applications?
Yeah, well, I mean, I guess I could just elaborate briefly on a couple of the things. So in a sentence about the verifiable computing getting used today in blockchain applications, I guess the thing people seem to be most excited about right now is something called a rollup. Very roughly speaking, the idea is that a public blockchain, like any computation, any work that the blockchain has to do, any data that's getting stored on the chain, that's like work that like every node in the network has to do. Like anyone trying to verify that the current state of the chain is valid. There's no invalid transactions in the entire history of the chain or something. Like everyone has to do that. So very roughly speaking, the idea is to treat the blockchain itself as a computationally weak verifier and then prove things to the chain. And that ensures that you're sort of minimizing the amount of work that these nodes have to do, that the blockchain has to do, while still getting the guarantees that there's nothing wrong with the data living on the chain. And it's a highly adversarial setting with potentially trillions of dollars being secured by the chain. So you need very strong guarantees that everything is kosher. So that's maybe just a brief elaboration on that. The streaming stuff without these sort of streaming algorithms, mergeable summaries, it's often just impossible to get real-time data, real-time answers to questions about your data. So, this library started at Yahoo. One of the first things they were using it for, if I'm remembering correctly, was to allow app designers to monitor in real time the number of unique users who have downloaded their app. And they previously had solutions that didn't use sketches, and you just could not get real-time information for questions like this. You bring out the sketches, you can. The answers now are approximate, but we we give very strong guarantees about how much error there is in the answers. So these are sort of the real life applications, just in a little more detail than before.
Yeah, and thanks for this. And definitely, it sounds really interesting about the verifiable computing. And I guess people are talking a lot about cryptocurrencies and blockchains nowadays. So that is definitely our readers, our viewers will go and maybe search on more on these topics. So taking a step aside from the technical questions, so let me ask you, when did you decide that you want to pursue a career as a researcher in theoretical computer science? Was there some particular event that pushed you towards it?
Yeah, so I was pretty fortunate to have a summer research experience after my first year of college. And it happened to be with a theoretical computer scientist. I did a project on extractors. It was really wonderful and fortunate. Actually, it's I believe that the computer scientist who was my mentor was the only theorist in his department. So it was really, just a whole lot of luck came together. I just loved it, and that was a fortunate way that I, decided this is what I want to focus on quite early. But there's been a lot of sort of happy accidents over time. My second summer of college, I did another research thing, and the project just sort of handed to me was on streaming algorithms. When I got to grad school, my mentor, Graham Cormode, from that summer, suggested some topic that was sort of at the intersection of what I was talking to my PhD advisor about and what he was working on. Turned out to be related to verifiable computing combined with streaming algorithms, where you really want the verifier to not have to store the whole input. And it was just one happy accident after another. I mean, obviously I enjoyed it, but that led to my whole PhD thesis because, so one day we submitted a paper on these streaming interactive proofs for review, and we get back a review that says, hey, you should look at this new protocol, an interactive proof for circuit evaluation, which I was totally unaware of, called by Gold-Rothschild and Rothblum. And my PhD advisor told me hey, you should implement this protocol, just to see how it runs, since we had implemented whatever little stuff we were doing in the streaming setting. And so, I told him, it's going to be totally impractical. The prover runs in cubic time. It's not, what's the point of implementing it? And my PhD advisor says, hey, just implement it. The worst case scenario is, you write in a paper, see, look how expensive the other approaches are. This is why you should be interested in what we're working on. And so I sat down to implement it. And, pretty soon I realized this cubic time prover could actually be made to run in linear time, just about linear time. So that's the jump from hopelessly impractical to potentially practical. So it was I think there are a lot of happy accidents along the way. But as long as you're studying things that you're interested in, so you're learning about a lot of stuff. It makes it more likely that these accidents might happen, and maybe they're not really accidents. Like maybe you're working on what you're interested in, you're learning a lot of stuff, and so you're going to notice things that people just haven't noticed before. So yeah, that's my rambling story for some of the things that happened to get me into this, and it's just been a really fun journey. I've been really fortunate.
Okay, yeah, that's quite pretty interesting story to listen to. So maybe as you said, there are like quite many happy accidents, and so just to give the particular example of you trying to implement a protocol, and suddenly you realize that it can be improved from n cube to n, the linear time. So maybe has it ever happened to you that you were working on some problem for maybe long time, and you got a result which was like not expected to you, and like how was the feeling?
Yeah, sure. So I guess I'll give one example of this. Something like this has happened. So, so with my work on approximate degree, when I was a grad student, I know, some researchers had just started developing a new technique to prove these approximate degree lower bounds. And I just kind of found it fascinating, and they hadn't proved significant new results yet. They were just hints that it was going to be powerful, and it just felt like a powerful technique to me. So I spent a long time kind of trying to understand the technique better. And what I was doing was I was going through the literature of known approximate degree lower bounds and kind of reproving the known results with the new technique. And typically when I was able to come up with the reproof, the new proof, it would actually prove something a little more general. So then I'd be able to claim like a new result. I knew I was like developing a better understanding for this technique, but it wasn't clear there's going to be like a major payoff for this. And it wasn't until so there was a particular barrier that we didn't know how to get past. And it wasn't until, I guess, 3 years ago. So, working on this for 7 years or something already, where we after 7 years of kind of studying this technique, we got past that barrier. And sort of, I guess it's maybe we're saying for anyone who's thinking about starting out in research or something, I just kept thinking about the same problem. I would have just go through the same line of thought over and over again, get stuck at the same point, just keep thinking, just a million times, just the same line of thought, and then eventually you just notice something, and that's kind of what happens. So 7 years in, I had noticed the thing, and by the way, so finally that's what took this approximate degree stuff, and for the first time since I was working on it, got new implications for quantum algorithms, because up until that point we were really just reproving results for that were already known, if at least the implications for quantum algorithms. So I think it's important to I thought it was hopeless. I thought it would take, I would basically never get past this barrier, and you just keep thinking about it. Don't lose hope, and one day you might just notice a little thing that you hadn't noticed before. So yeah.
Okay, I mean that would be like 7 years. It's quite a long time. Okay. So so maybe just building upon that question only. So you said like there were 7 years and you're trying to think on the same same line of thought, and you couldn't like notice that small thing, but in the end you were able to notice and cross that barrier. So according to you, what is the hardest part of doing research, and any advice on how to do better in that?
Yeah. So I think if you ask this to 10 different researchers, you're going to get 10 different answers, but that means I can indulge myself, however. So, I think just the startup, the ramp up is just intimidating. Everybody is intimidated by this, because until you've you've produced some results, you just feel like you're like, am I going to be able to do this? Some huge percentage of people have imposter syndrome. I think my advice is to dive into the literature. Like the ideal situation, I think, is to find a topic you're interested in, and sort of understand very deeply what's known about that topic, like the state of the art. Then you're ready to work on the open questions. And this can be a very hot area that just has huge numbers of people working on it at that time. Might be a little more challenging, high stress area to apply this to. There can be sort of benefits to finding something that catches your interest, that you kind of, maybe you have some intuition, like, this is, if we could understand this a little better, it could have significant payoffs. But yeah, when I was sort of starting out myself, there were a bunch of happy accidents along the way, but I tried to just learn about a lot of areas, so maybe I'll say, people just starting out, I think it's kind of scary. You're like, there are all these senior people out there. Surely they must have thought about this problem. And if they didn't make progress, how am I going to make progress? And to that, I'd say several things. One is that there's just so many questions, so much progress to be made, that I no matter how many people we have with years of research experience working out there's always going to be stuff that they're going to miss, for sure. But more than that, as people sort of get more experience and more senior, they develop, obviously their breadth of knowledge might keep expanding, and research is a skill, and they just kind of get better at it. They can read papers faster and understand them faster and things like that. But there are also downsides that come with it. You can get stuck in a way of thinking, so some new approach might be needed, and I've spent like a decade, understanding like certain techniques, and to come up with a totally different approach now, I'm probably at a disadvantage compared to someone just starting out. I think that just getting started is probably intimidating to everyone. So no, you're not alone in that. And just dive in, and you have many advantages over the other more senior people you might be intimidated by. You have fresh eyes. It's exciting to be learning so much. If you want to obsess over a problem as a grad student, you might have more time to do that than someone more senior who has, whose job isn't like just to learn and do research all day. This is probably worth the amount you're paying for it, but that's my view on the hardest part of research, and my thoughts on how you might overcome it. Yeah.
Okay, thank you for this beautiful advice. And as you rightly said, as a grad student, you will have a time to obsess over the problems, and I think it's really a very important fact for all of us who are going to grad school sometime soon. So maybe changing gears, and just on a side question. So, as we can see, that doing research is quite a difficult job. Maybe you like it, but you need a lot of patience and hard work. So, how do you take a break from all of this? What do you do for your recreational activities?
Yeah. So I historically I like to run. Like that's sort of my way of making sure I'm not looking at my phone, which I will look at every 5 seconds if I'm near it. It's literally the only time I'm probably away from my phone. These days, I have a 4-month-old at home, so whether I want to or not, that's a frequent break from research. Let's put it that way. So that's great. I'm always talking to my friends, which is probably actually a huge distraction because it keeps me tethered to my phone and all that. I think it's super important to have some balance in one's life, and it can be hard to do, but I think you're going to be a more productive and just generally happier and healthier researcher if you make sure you make time for these other things. So my particular hobbies are maybe not so excited, running and hanging out with my baby. But yeah, these things are super important, and we all struggle with this sort of balance thing. So I'll maybe do what I say, not what I do, but make sure you don't compromise on that. Yeah, you can always spare several hours every day to do what you like outside of work. And I think you're going to be better off for that in all ways.
Right. So maybe I would like just to re-emphasize the statement that people should have balance in their life. Usually we students are like quite burdened with work, and we think that okay, we shouldn't take breaks and we should work as many hours. Like productivity is like equivalent to hours of working. So maybe, but as you said, with some breaks, the productivity increases. So that is a really good statement. So maybe wrapping things up. So just a final advice for our audience who are in their first steps to become researchers. What should they do so that they enjoy the research they're doing, and maybe how to get better in that?
Yeah. I mean, so I think number one, work on something that really catches your interest and that you're excited about. Like I think if you find yourself obsessing over a problem, like that's a great sign. If you never experience that, I'm guessing that's not such a great sign. So there might be temptation to like go into some particular hot direction. I would suggest to maybe resist that. So with some of my work, sort of the value of the work didn't become clear for a long time. I mean, I haven't been around that long, but for example, this paper I mentioned with the taking something that was cubic time and making it linear time. Actually, the first time we submitted that, it was rejected. As I was trying to understand this new technique for approximate degree and sort of methodically reproving the old results, those papers got rejected left and right. So don't get discouraged by that. Like if you have conviction that you're understanding something better that matters, you should maintain that conviction, even if other people aren't immediately recognizing the value of what you're up to. I think this can be particularly challenging for beginning researchers if you find yourself in a position like this, because when you're just starting out, sort of the variance is hitting you harder. Like you haven't had a long period of time for like the ridiculous randomness in like paper decisions, except reject decisions, to sort of even itself out from the law of large numbers. And this can frustrate people, be discouraging to people. This happens to everyone. It's just important to enjoy what you're doing, to find it obviously interesting yourself, and to not get discouraged if you wind up in such a situation. And just dive in. The big advantages of grad students, fresh eyes, learning a lot. So just making connections between things that someone who's been around a long time is just not doing, because they're not learning so much and spending so much time on the research because they can't. Those are my general pieces of advice. There's a lot that just the nature of the system, probably any system, there's going to be randomness. The randomness is going to sort of hit the people just starting out the hardest. It's almost unavoidable. It's really unfortunate, and just don't get discouraged. This happens to probably everyone. Obviously some people can benefit from the randomness, just as other people can struggle with it. So I just want to kind of offer that reassurance. I was quite frustrated with this early on. And I'm thrilled with sort of where I am now. And I'm glad that I didn't let the frustration sort of get to me too much. And I just want to, if anyone finds themselves in a similar situation, I want them to appreciate that.
Okay. Thank you, Professor Justin, for this beautiful advice. The line which you said about randomness hits, there's a lot of randomness, and randomness hits the early researchers the most. I guess it's a very important line for all of us, that we shouldn't be discouraged from maybe paper rejections or something. If we are enjoying what we do, then it's a good sign. So maybe I will conclude this session with this. Thank you, Professor Justin, for all the beautiful advices and explaining the research topics. So for our audience, if you are interested in this areas of verifiable computing and approximate degree, please definitely check out Professor Justin Thaler's webpage. There are quite nice surveys on this. He has taught some courses on also on that. So definitely do check out on these topics. And thank you, Professor Justin, for taking time on your Saturday morning and talking to our lovely audience. Thank you once again.
Thanks for having me. Yeah.